for the introduction and for the opportunity to present today. And good afternoon. Today I'll be talking about carbon nanotube FET transistor to detect nitrogen dioxide. I'll begin with an overview about the carbon nanotube transistor and how it works as a sensor. Then I will talk about our feature extraction method to extract features from transistor characteristics, and then I will show some experimental results. Nitrogen dioxide, or NO2, is a gas, a pollutant gas, and it's particularly harmful for the environment and for the human health. And for instance, in this table, you can see the maximum exposure limits set by some directive from European Union and US. And you can notice that all of these limits are in the ppb range, part per billion. These are really low concentration values. And this means that we need a low detection limit sensor. A possible good sensing material for that is carbon nanotube. And carbon tube is a nanomaterial, a tube-shaped nanomaterial. And the surface is made by a single layer of carbon atoms. And when nitrogen dioxide adsorbs on its surface, it changes its electrical properties. We use this in a transistor, where the carbon nanotube is the channel of the transistor and is suspended between source and drain electrodes. And this device has already proved to be low power and to have a low detection limit. So now you can see the cross-section of our transistor, where the gate is beneath the carbon nanotube channel. And what we do is to measure the transfer characteristics of this transistor, which is the current measures over different gate voltages. And when nitrogen dioxide starts absorbing on the device, this curve changes, as we can observe in the animation. And for instance, here you can see the difference at 0 NO2 and after the absorption of 10 ppb of NO2. In this second graph, you can see the difference of the transfer characteristic with increasing NO2 concentration. Overall, we have an increase of conductance with a curve tilt, but also a threshold voltage shift. So now I will talk about the feature extraction method from this transistor transfer characteristics. Here you can see another example of our carbon nanotube transfer characteristics, and what people in literature, but also we did in our previous studies, was to focus only on a single feature from these transfer characteristics. For instance, we only try to extrapolate the threshold voltage over time, and then others, maybe they tried also to calculate the current in the on state, so the current at the maximum conductance points, and others, they only considered the transconductance, which is defined as the current slope in the on region or in the linear region in our case, or others, they focus only on the subthreshold swing, which is defined as the inverse of the slope of the current at the logarithmic scale in the region below the threshold. Now, however, what we want to do now is to not focus in a single feature from this, but to extrapolate all of them, and in such a way that we can fully capture all the changes happening in the curve. To do this, we recently developed a new feature extraction method that we called physics-informed autoencoder. But first of all, what is an autoencoder? Basically, it's a type of neural network architecture that is widely used for dimensionality reduction or feature extraction, because it decodes the input in a compressed representation, and from it encodes back to reconstruct the input data. What we do now is to take the transfer characteristic as input, and then the encoder extrapolate 4 numbers. That they are not, these 4 numbers are not mathematical abstract representation, but they are really 4 physical parameters corresponding to the 4 transistor parameters: the threshold voltage, the current in the on state, the transconductance, and the subthreshold swing. And then the decoder from these 4 numbers decode the transfer characteristics in output. And you can see that the reconstruction in general is really good. which means that these four numbers are really capable of taking all the information contained in the transfer characteristics. So now that we have the feature extraction method, we are going to analyze these features extracted through a gas experiment. Here you can see the time setting of our gas experiment, where we change NO2 concentration in increasing step from 0 up to 150 ppb, and then we decrease it back to 0. And for each NO2 setting, we also change the water vapor content, and this corresponds to 0, 20, 40, 60% of relative humidity. So in this gas mixture experiment, if we take the first half of the experiment, we can see that how the curve changes upon nitrogen dioxide increasing, and also at the same NO2 concentration, how humidity affects the curve. And in general, we have a slight decrease of conductance with increasing NO2 concentration for humidity. In this second half of the experiment, you can see that the transfer characteristics change like this, for instance. And one thing that you can immediately notice is that the change is not so evident as before. This is because when the absorption and the desorption of NO2 on the device is a different rate. So if the nitrogen dioxide absorbs really good and really fast, the desorption is much more slower. This is why we have this. And, no, sorry. So you can see that in general, this experiment is particularly challenging because we have NO2 increasing but also decreasing, and also because we have humidity as interferent. Oh, sorry again. And what we want to do now is to not take all the prediction, all the results at each time interval, but actually we want to take only the measurements taken at the last minute before each gas concentration setting to avoid the gas settling times on the measurements chamber. So now during the whole experiment, we extrapolated the whole feature in time. And first of all, we conducted a correlation analysis. And you can see here in this graph that all the features are strongly correlated to each other, and in particular, the transconductance is linearly dependent to the current in the on state. This is why in the next analysis, we will only consider three features: the threshold voltage, the transconductance, and the subtraction swing, because we believe that the on-state current will not bring additional information. So now, first of all, we try to predict NO2 in this gas mixture experiment, but this time only considering one feature at a time, and we use a nonlinear algorithm, the kernel ridge regression with a Gaussian kernel, and we split the data set in a training set and test set. And here you can see the results on the test set for each feature. And the plots are showing the prediction versus the real values, where the red line represents the ideal prediction curve. And you can see that the threshold voltage is the feature that best that has the best results in predicting NO2, as can be observed also on the prediction scores, like, for instance, the mean absolute error. And next, now we try to predict NO2 using all of the features, so three features instead of a single one, with the same algorithm in the gas mixture. And now we obtain results like this. You can immediately see that the prediction results are definitely improved. And for instance, the mean absolute error is now at 8.7 ppb, while before using only the threshold voltage was 14.9. And actually now, even if we have only one sensor, but we have more features from it, we actually trained this algorithm to not predict only NO2, but also to try to predict humidity. And these are the prediction results for humidity. And the mean absolute error in this case is 1.6 per thousand, which corresponds to a relative humidity of 6.8% of mean absolute error. So now, conclusion. I'll show you how our carbon nanotube sensor works, and I used this sensor in a gas experiment where we have absorption and desorption of the gases and with different humidity values. And we demonstrated that using more feature in the transfer characteristic of this transistor can definitely improve the prediction performance. And even if using one device, we are somehow able to predict two gases in a gas mixture. In the next, we plan to do also ozone measurements, because we know that ozone is generated in an environment with nitrogen dioxide and UV light. And also, we are working currently in a different type of algorithm which also take care of the dynamic response of the sensor. In such a way, we could predict nitrogen dioxide at each time instant, or at least at regular time intervals. Now, I would like to thank my research group, the Micro-Nanosystem group at ETH in Zurich, and Dr. Mira Lushka, my student Marco Paye, and my carbon nanotube gas sensor colleagues, and the technical facilitator from First CLA and BMC clean room. Thank you very much for your attention, and I will be glad to answer to possible questions you might have. Thank you.